Let me ask you something. Right now, while you're sitting there, how many things is gravity doing? Not out in space, not at the center of a black hole. Right now in this room, to your body. Most people say one thing. It's pulling me down, keeping me in my seat. And yeah, that's true. But that answer is so incomplete, it's almost a lie. Gravity is doing hundreds of things to you right this minute, and you don't notice any of them, the same way a fish doesn't notice water. Gravity is compressing the cartilage in your spine. It's pulling your blood downward, so your heart has to work harder to push it up to your brain. It's pressing the air against your eardrums. It's holding a column of atmosphere above your head that weighs roughly 10,000 kilograms. It's keeping the nitrogen and oxygen molecules you're breathing from drifting off into the vacuum of space. It's pressing the tectonic plate beneath your feet against the hot mantle underneath. It's bending the path of the earth around the sun so you don't fly off in a straight line into the dark. It is right now making time tick slightly slower for you than for someone standing on top of a mountain. That's not poetry. Every one of those is a measurable physical effect. You live inside all of them every moment of your life, and you've never once felt them. So here's what I want to do. I want to peel this thing apart one layer at a time, starting from the simple and going deeper and deeper. And once you see all the layers, once you see the full portrait of what gravity is actually doing, we're going to do something reckless. We're going to switch it off. 1 second, just one tick of the clock, and then we're going to see what breaks. I promise you, it's stranger than you think. All right, layer 1, the obvious one. You're standing in a room. Gravity shuts off. What happens? You float. Obviously, your feet leave the ground. Everything on the table, the cup, the pen, the salt shaker, they all just drift upward a little bit. It's like being on the space station. Fun, right? Weightless. Like a dream where you can fly. Now hold on. I said drift upward. But why upward? If gravity is gone, there's no up and down anymore. Those words just lost their meaning, so why would you float up instead of just hovering in place? Here's the first thing people miss. You wouldn't just hover. Right before gravity turned off, the floor was pushing up on your feet. Newton's third law. You push down on the floor pushes up on you. The forces are balanced, so you stand still, but both forces are real. The instant gravity disappears, the downward pull vanishes, but the upward push from the floor doesn't vanish at the same instant, because your feet and the floor were slightly compressed, like tiny springs. They uncompress, that gives you a little kick upward, very gentle but real. More than that, your body was making constant micro adjustments to stay balanced. Tiny muscle contractions in your legs, your ankles, your core, all of those were calibrated to fight gravity. The signals from your brain to your muscles travel at about 100 meters per second. It takes a few hundredths of a second for the gravity is gone news to propagate through your nervous system. In that fraction of a second, your muscles are still firing anti-gravity corrections. They push you in odd directions. You might tip forward. You might lean. Someone mid-stride would tumble because the whole walking motion is a controlled fall that depends on gravity being there to catch you. The blood in your veins is being pumped upward by your heart against gravity. Suddenly, there's no gravity to pump against. The blood pressure in your head spikes slightly. Your face flushes. The blood in your legs, which gravity was pulling downward, redistributes upward. This is exactly what happens to astronauts, by the way. Their faces get puffy, and their legs get skinnier. They call it chicken legs and moon face. In 1 second, you wouldn't see much change, but you'd feel it. A rush to the head. A warmth behind your eyes. And your inner ear, the vestibular system. You have these little chambers filled with fluid and tiny calcium carbonate crystals called otoliths. When you tilt your head, the crystals shift under gravity, pressing against hair cells that tell your brain which way is down. Remove gravity and the otoliths float. The hair cells get no signal. Your brain, which has relied on this signal every moment of your life since before you were born, gets confused, deeply confused. The room seems to spin, even though nothing is spinning. You feel nauseous, disoriented. Some people would stagger. Some would grab onto furniture. It's the same sensation you get on a roller coaster at the top of a drop, multiplied by 10. Every animal on Earth with a vestibular system, which is essentially every animal with a backbone, feels this simultaneously. Birds in flight would be the most affected. A bird's sense of up and down is even more critical than yours. Their flight depends on it. A pigeon mid-wing beat would tumble. A hawk diving for prey would veer off wildly. Fish in the ocean would lose their sense of which way is the surface. Even insects, which use gravity-sensing organs called statocysts, would wobble. And think about the plants. This one is subtle. Plants know which way is down. Their roots grow downward, and their stems grow upward because of a process called gravitropism. Inside their cells, tiny starch granules called statoliths settle to the bottom under gravity, triggering chemical signals that tell the plant which direction to grow. Remove gravity, and the statoliths float. The chemical signals stop. The plant's growth compass goes blank. For 1 second, every root tip and stem tip on Earth briefly loses its sense of direction. This doesn't matter, of course, because 1 second is far too short for any visible growth. But at the cellular level, the chemistry hiccups. A tiny molecular stutter in every plant on the planet, all at once. I love that. A moment of collective botanical confusion. 1 second of weightlessness. Unpleasant for animals, imperceptible for plants, survivable for everyone. You might spill your coffee, though. The coffee, by the way, does something beautiful. It lifts out of the cup in a perfect sphere because without gravity pulling it down, the only force shaping the liquid is surface tension. And surface tension always wants to pull a liquid into a sphere. For 1 glorious second, there's a little ball of coffee hovering where your mug used to hold it. Then gravity comes back and it splashes everywhere. But for that 1 second, it's magnificent. Alright, so that's layer 1. Floating people, floating coffee, confused inner ears, the part everyone imagines. Most people stop right here and think they've answered the question. They have not even begun. Let's step outside. The air you breathe. Why does Earth have an atmosphere at all? This is a question most people never ask, because the air has always been there, but it doesn't have to be. The moon has no atmosphere. Mercury has essentially none. Mars has a thin wisp. Why does Earth have this thick, rich blanket of gas? Gravity. Gravity holds it down. An air molecule, let's say nitrogen, which makes up about 78% of our atmosphere, is not sitting still. At room temperature, a nitrogen molecule zips around at about 500 meters per second on average. That's fast. Very fast. About 1100 miles per hour. Faster than the speed of sound, actually. Every molecule in this room is a tiny bullet ricocheting off the walls, off the floor, off other molecules, billions of times per second. Why don't they all fly away? Because the escape velocity from Earth's surface is about 11.2 kilometers per second, which is 11,200 meters per second. The average molecule is moving at 500. That's way below escape speed. But here's the thing. That's the average speed. In any gas, there's a distribution of speeds. Some molecules are slow, some are fast, and a tiny fraction are really fast. This is called the Maxwell-Boltzmann distribution. And the tail of that distribution reaches up to very high speeds. At any moment, a tiny fraction of air molecules near the top of the atmosphere do have enough speed to escape. And they do escape. Earth is slowly losing atmosphere right now. Today, just very, very slowly, hydrogen and helium, being the lightest, escape the fastest. That's why our atmosphere has very little hydrogen compared to the universe as a whole. So gravity's job is to keep the escape rate negligibly small. It's the leash on a billion energetic dogs. Cut the leash for 1 second. What happens? The entire atmosphere doesn't vanish. Not even close. In 1 second, even the fastest molecules can only travel about 10 to 15 kilometers. The atmosphere extends up hundreds of kilometers, and the bulk of it is in the lowest dozen or so. So the lower atmosphere mostly stays put out of sheer inertia. It hasn't had time to go anywhere. But 2 things do happen. First, the pressure gradient starts to dissolve. Right now, air is denser at sea level and thinner as you go up. This is because gravity stacks the air, compresses the bottom layers under the weight of all the air above. At sea level, the pressure is about 101,000 pascals, about 1 atmosphere. At the top of Mount Everest, it's a third of that. On an airplane at cruising altitude, it's a quarter. Remove gravity, and there's no reason for the air at the bottom to be more compressed than the air at the top. The atmosphere begins to equalize. Dense air at the surface starts to expand upward. Thin air at high altitude doesn't get replenished by subsiding gas from above. In 1 second, the change is tiny, maybe a few pascals drop at the surface, but it's measurable. Sensitive instruments would pick it up. Second, at the outermost edge of the atmosphere, the thermosphere and exosphere, where molecules are already spread incredibly thin and some of them are moving fast enough to barely be bound, those molecules leave. They're gone. They reach escape velocity because the velocity required to escape just dropped to zero. Any upward motion at all is enough. Earth permanently loses a thin shell of its outermost atmosphere. Not enough to notice in your daily life. Not enough to change the air pressure you feel. But it's gone. Irreversibly. And here's a beautiful subtlety. Weather patterns are driven by pressure differences. High pressure zones and low pressure zones. Wind is air moving from high to low pressure. If the global pressure field shudders, even slightly, it sends a ripple through every weather system on the planet. 1 second of gravity off wouldn't create a hurricane. But it would nudge existing storms. It would create a tiny perturbation in the atmosphere that would propagate for days, altering weather forecasts in ways too small for anyone to trace back to the cause. The butterfly effect, except the butterfly is an entire planet hiccuping. Layer 3. The oceans. Water is heavy. A cubic meter of seawater weighs a little more than 1,000 kilograms. The total mass of the ocean is something like 1.4 times 10 to the 21st kilograms. All of that water is held in its basins by gravity. Every drop in the Pacific, every molecule in the Atlantic is being pulled toward the center of the Earth. That's what gives the ocean its shape. That's what makes the surface, on average, follow the curve of the planet. Kill gravity, and the ocean is no longer being told to stay put. But the ocean wasn't just sitting there even before gravity turned off. Currents move water constantly. The Gulf Stream carries about 30 million cubic meters per second, flowing at maybe 1.5 to 2 meters per second in its core. The Antarctic Circumpolar Current, even bigger, moves 150 million cubic meters per second. Tides were pulling water toward the moon and the sun. Waves were cresting and crashing. All of that momentum doesn't vanish when gravity turns off. The water keeps moving in whatever direction it was already going. But now there's nothing pulling it back to the surface. A wave that was cresting at the moment gravity stopped, it keeps going up. The spray off the top of that wave just keeps flying. Coastal waters that were pressing against the shore relax. Not dramatically, not like a movie tidal wave in reverse, but subtly. You might see the waterline creep back 0.5 centimeter on a beach. You might see a strange bulge form on the open ocean where two currents converge and the water, with no gravitational pressure holding it flat, heaps up ever so slightly. And here's something that sounds like science fiction, but is pure physics. The ocean floor is under tremendous pressure. The deeper you go, the more water stacks above you and the more crushing the force. At the deepest point, the Challenger Deep in the Mariana Trench, the pressure is about 1,100 atmospheres. That's over 1,000 kilograms on every square centimeter. Like having a small car balanced on your thumbnail. That pressure exists because gravity pulls the water down and stacks it up. Remove gravity, and the weight disappears. The pressure starts to drop. Now, it doesn't drop instantly everywhere. Pressure changes travel through water at the speed of sound, which in seawater is about 1,500 meters per second. The Mariana Trench is nearly 11,000 meters deep, so it takes about 7 seconds for the gravity is off message to reach the bottom. In our 1 second, the pressure relief only penetrates about 1,500 meters down. But in those upper 1,500 meters, here's what happens. Dissolved gases come out of solution. Seawater has dissolved nitrogen, oxygen, carbon dioxide. The amount of gas that can stay dissolved depends on pressure. Lower the pressure and the gas starts forming tiny bubbles. This is the exact same physics as opening a bottle of champagne. You release the pressure and the dissolved carbon dioxide forms bubbles and rushes out. In 1 second, the effect is tiny. Microscopic bubbles forming at maybe a few hundred meters depth. Nobody on the surface would notice. But if you were diving at 30 or 40 meters, you might see the water around you start to fizz. Just slightly. Bubbles appearing from nothing. An eerie quiet effervescence in water that was perfectly clear a moment ago. When gravity comes back, the pressure snaps back to normal, and those bubbles collapse. But some of the gas might not redissolve immediately. For minutes afterward, the ocean would be very slightly more bubbly than usual. Tiny microbubbles persisting in the water column, layer 4. And this is where people start to feel uncomfortable. The ground beneath your feet. The Earth is not a solid ball in the way an iron cannonball is solid. It has structure, layers. The crust, the outermost layer, is thin. Under the continents, maybe 30 to 50 kilometers thick. Under the oceans, just 5 to 10. Below that, the mantle, nearly 3,000 kilometers of rock, that behaves like a solid over short timescales, seconds, minutes, but flows like an incredibly thick liquid over millions of years. Below that, the outer core, liquid iron and nickel, churning with convection currents that generate Earth's magnetic field. And at the very center, the inner core, a solid ball of iron about the size of the moon, squeezed into solidity by unimaginable pressure, roughly 360 billion pascals. Every one of these layers exists because of gravity. Gravity sorted them. The heaviest stuff, iron, sank to the center during the early molten period of Earth's formation. The lighter silicate rocks floated to the top. That's why we have a metal core and a rocky crust. Gravity organized it by density, and gravity keeps it organized by maintaining pressure. The inner core is solid, not because it's cold, it's actually extremely hot, about 5,000 degrees Celsius, as hot as the surface of the sun, but because the pressure is so enormous that the iron atoms are forced into a solid crystal structure despite the heat. Remove gravity, and what happens to this structure? In 1 second, not much changes in the deep interior. The speed of sound in Earth's core is about 10 to 11 kilometers per second. In 1 second, the no-gravity signal can penetrate about 10 to 11 kilometers into the Earth from the surface. That doesn't even get through the crust in most places. The mantle, the outer core, the inner core, they have no idea gravity is gone. They're still under the same pressure, still in the same state. But the surface, the crust, that top 10 kilometers or so, that changes. Right now, the crust is under compressive stress from its own weight. Rock layers are pressed together. Faults, the cracks where tectonic plates meet or where stress has fractured the rock, are held shut by the weight of the rock above them. Geologists call this lithostatic pressure. It's like putting a heavy book on top of a stack of paper. The paper can't slide because the book is holding it down. Take the book away, and the sheets can slip. In that 1 second, the top several kilometers of crust